Pleasure to be here, and let me just start right in. But before, well, I'm not going to start right in. This is a picture of the Earth's atmosphere. Most of the Earth's atmosphere is only 90% of the Earth's atmosphere is less than 10 miles high. And so this is kind of a reminder of this is where life is for the most part, and it's very, very thin and more fragile than we thought. So I'm going to be talking about the risks of climate change very briefly, and then how science and innovation can really make clean energy and a clean environment a low-cost option. So first, the risks. Very quickly, between 1880 and 2017, 2016, the average land temperature and sea surface temperature of the Earth has been rising. But I do want to emphasize that most of this has occurred only since 1975. So it's a recent phenomenon. You can ask a question, are the glaciers melting? Is the sea level rising? And the answer is simple, it's yes. It's being measured by satellites now with astounding accuracy. And as a matter of historical fact, in the last warm period, over 100,000 years ago, the Earth was only 1 degree warmer than it is today. But the sea level was 69 meters higher. And we knew this for a while, but we thought it would take thousands of years for this to happen. And now while watching Greenland and Antarctica melt with increasing speed, there's a great concern that perhaps it would take less than 200 years. So here's a recent paper of recalibration of sea level melts going to 2100. The red is the business as usual scenario. It's not quite business as usual, but it does say we cap and bring to a halt greenhouse gas emissions in 150 years. But we are on the red line. But if you extend beyond 2100, you see that the sea level continues to increase, and this is 5-meter level. So what we think also would be happening at a much shorter time scale is happening today is that water aquifers are being depleted in many parts of the world. And we see increased crop failures and rising seas, so we anticipate more climate refugees. And 700 million people live within 10 meters of sea level. So we saw what happened, or had seen what happens when you have 3 or 4 million refugees who want to come to Europe from both Syria and North Africa. And then you can try to imagine what would happen if it's not 3 or 4 million refugees, but maybe 30 million or maybe 300 million. A big fear of India is that many tens of millions of refugees from Bangladesh would go to India, and they really have no plan for what to do except build a wall. And so this is what perhaps we're looking towards. Cumulative emissions of CO2 are important. It's not the yearly emissions, because once you throw carbon dioxide into the atmosphere, aside from immediate pickup of carbon dioxide in the ocean and land with about a 10-year time scale, most of it just circulates between land and atmosphere, ocean and atmosphere. So for that reason, it's cumulative amounts that continue. The other time constants are greater than 30,000 years. So we're now over 400 parts per million CO2, whereas the UN goal is to keep below 450. This is the cumulative emission where we are. The UN goal is that red line at 2,900 gigatons of CO2. And the father of Taoism said something very wise. If you don't change direction, you will end up where you're heading. Again, the cumulative emissions occurring only in the last 3/4 occurring only in the last 65 years. Okay, so this is these risks are of some concern, a lot of concern. So let's talk about how science and technology can make a real difference. The first is energy efficiency everywhere, in transportation, industrial processes, building cities, agriculture. Much of it is technology we already know, but we're not really using as much as we can. I should also point out that agriculture, land use, forestry, grazing land, accounts for roughly 30% of all carbon emissions. That is comparable to the amount of greenhouse gas emissions that are in the electrical generation sector. Okay? Agriculture, land use, grazing, same as electricity generation. Restoring carbon in the soils has the potential to sequester 20 gigatons of carbon dioxide, about 8% of all the cumulative emissions that have occurred so far. If you actually start to do better agricultural practices, low tillage, things of that nature, you can put this carbon not only back in the ground, but you increase agricultural productivity. We haven't been doing this. It's been going the reverse way. That there are methods we know to do this. If you think about how many how much carbon dioxide plants, agricultural plants and grazing land plants fix, minus the respiration of the CO2, it's actually considerable. It's more than the total emissions. It's 1.5 times the total emissions of human emissions of carbon dioxide. And so understanding the interactions between plants and the soil microbes is really a new frontier in science. Just as we're beginning to understand that the microbes in our gut have a very profound impact on our immune system, on our cognitive abilities, even our ability to recover from stroke, which was unimaginable a decade ago, we're beginning to realize that the tens of thousands of different soil microbes have a very symbiotic relationship with the plants, and they are very helpful in bringing in plant nutrients in some perennial plants and fixation of nitrogen and so on. And there is a big opportunity to increase food productivity and restore soil fertility by reintroducing carbon into the soil. So that's, I think, something that many of you should look at as a wide open future opportunity. Now, renewable energy costs are plunging around the world, and they're likely to go below 3 cents a kilowatt hour by 2020 and less than 2 cents a kilowatt hour by 2030. So what's the evidence for this? This is a graph. Each circle is an actual contract of a wind farm in the United States. The purple contracts are the great expanse of wind from North Dakota to Texas. And these are now hovering at 20 cents a megawatt hour, $20 a megawatt hour, 2 cents a kilowatt hour. Considerably cheap. Well, it has a subsidy to be sure, but even without subsidy, getting very, very competitive with natural gas generation of electricity. And natural gas generation of electricity in the United States is actually 3 or 4 times less than in Europe. Great Britain offshore wind contract very recently, 57 pounds per megawatt hour. Astounding price considering it's offshore wind. And solar auctions in the best sites around the world are dipping below $30 a megawatt hour without subsidy. All right. This is all very good because that means these prices are becoming competitive with the cheapest forms of fossil fuel. But it's not the full price. The full price includes all the backup generation you need when the wind doesn't blow, the sun doesn't shine, and a very enhanced transmission distribution system and energy storage, so important that there seem to be 2 ands. In any case, there is an increased challenge for integrating these intermittent sources of energy, wind and solar, and distributed sources into a grid. So you have centralized generation, you have distributed generation, you have sources turning on and off due to changing weather. And it's going to be very complex. I might also add that despite the current administration of the U.S. government, not everybody believes in where he wants to go. I live in the state of California, and in 2016, 29% of electricity was renewable, and the 2030 California goal is to go to 50%. Not generating capacity, actually electricity used. And so we're being very aggressive. But how do you manage this complex electrical system? And so I want to tell you about the ability of a machine, AlphaGo, to play the game of Go. This was the world champion after his first match, or during his first match. Before the match, he looked at the computer who played the Korean champion a year before. He looked at the game and said, I can beat this computer. And he started to play in his first match and said to himself and to others, this computer is not playing like it did 1 year ago. And what happened? Well, the people in AlphaGo programmed the computer to play itself. And without human expert intervention, it just played itself over and over again and learned from playing. And it just went beyond any human experience of how to play Go. And so the former Go champion said, AlphaGo sees the whole universe of Go, while I could only see a small area around me. It's like I play Go in my backyard, while AlphaGo explores the universe. Unstructured machine learning has also been used to do translations, and Google Translate actually flipped the switch a year and a half ago. The translation got markedly better. All the human expert people who were helping Google Translate were told, go find another job. The machine is doing better than you. Thank you very much. And so machine learning, unstructured machine learning, can also be used to automatically manage electricity distribution and learn to forecast energy use, including more accurate forecasts of weather. So let's go to energy storage. When you think of energy storage, you think of batteries. This is a chart of plunging batteries, prices of batteries for electric vehicles. And this chart was made in 2014. Those gold symbols were projections of where electric vehicle batteries might be. The Tesla Gigafactory, when it's built, is projecting they will be able to produce the manufactured battery packs at $150 a kilowatt hour, well below what we thought were optimistic projections. And remarkably, General Motors has said very recently that their electric vehicle battery cells will be at $100 a kilowatt hour by 2022. So great progress, slow, steady progress. I think you'll hear more about it in one of the talks going forward. But let me show you a picture of the best form of energy storage that I know about. Here it is. The way it works is when the wind blows, you pump water. And so the energy needed to pump water is already done. When you need the water, you open the valve. A modern-day version of this is being planned in northern Chile. In the coast of Chile, there's a cliff 660 meters above sea level, very, very close to the ocean. So they're planning a 600 megawatt solar farm. In addition to that, they plan to pump seawater from the ocean up into reservoirs 600 meters high. The estimated cost of installing this generation capacity will turn out to have an average energy cost somewhere around $7 a kilowatt hour. And so let me remind you, the chemical battery systems projected in the next 10 years hope to reach $100 a kilowatt hour manufacturing costs. So pump storage will remain an order of magnitude cheaper than chemical batteries, I think, in the foreseeable future. Because of that reason, pump storage is being recognized as being a good source of storing wind and solar energy. And so these lines, the blue, the green, and the orange lines, are lines connecting mostly Norway, a little bit of Sweden with us and Iceland, to the batteries. Where are the batteries? Well, they're in Norway because of your interlocking hydroelectric dams. And so Norway wants to follow Switzerland's example. And when the wind blows, they bring cheap wind energy to pump water from one dam to another. And the next day, when you need electricity, they sell it back to you at 2 or 3 times the price. Switzerland does this. They buy cheap nuclear energy at night. In the daytime, they sell to Italy at 3 times the price. Very, very Swiss. So in any case, so these are plans. Now you notice the light blue is under consideration. And the light blue connects North Africa to Europe. North Africa has some of the greatest solar in the world, and it's under consideration, not under planning, because they have to resolve some energy security issues. You don't want to be stripped of electricity for a week, a month, or a year. So going on, electric vehicles. I hope you will hear about electric vehicles. But let me tell you about the electric vehicle forecasts. There are 2 forecasts, 2015 and 2016, and they look slightly different. The 2015 electric vehicle forecast from 2020 to 2040 is shown in dark blue. 1 year later, people are forecasting a 5 times more aggressive sales forecast. And China has targeted that 11% of all new car sales in China, they want to be electric vehicles. And by 2032, there should be, or they want to have 70 million EVs on the road. Why has this forecast been changed so dramatically in 1 year? Was there a battery breakthrough? And the answer is no. So let me bring you back a century to explain what's going on. In the 1890s, in American cities, transportation was via horse-drawn carriages. Within 30 years, there was a remarkable shift. No more horses, electric trams, and cars. And so you can say, sure, automobiles, better technology. But if you think about it, it required a completely new infrastructure. It required better roads. It required an oil, gasoline supply chain, repair shops, everything. And so to actually completely change the infrastructure from horse to automobile takes a lot. Very, very rapid change. But there was one thing that was really pushing it, and that was an environmental pollution problem. What was the pollution problem? Well, 160,000 horses in New York and Brooklyn in 1880 were producing 3 to 4 million pounds of horse poop a day. It's a technical term that physicists use. And it was piling up everywhere in vacant lots, 1 story high. It was all over the streets. You couldn't walk across the street unless without getting horse manure ankle deep, unless you had a young urchin who was willing to, for a small payment, sweep the street for you so you can walk across. Okay, so because of this very rapid transition, because there was a cleaner source of transportation, okay, fast forward 100 years. This is Beijing on a bad air day. And we are discovering the particulate matter, that's PM 2.5 especially, this is particles less than 2.5 microns in diameter, are extremely deadly. In 2013, there was a Lancet Oncology study which had enormous number of people, 300,000 people followed for 12.8 years, and 2,100 incidences of lung cancers were diagnosed, and they found for every 5 micrograms per cubic meter of PM 2.5, there's an 18% chance higher, 18% higher chance of getting lung cancer. All right. What's Beijing's average air? Well, it's 76 micrograms per cubic meter. And so now this risk of lung cancer with exposure begins to saturate. Not everybody who smokes 2 packages of cigarettes a day get lung cancer, but you're 25 or 30 times more likely to. Now, the World Health Organization guideline is currently 10 micrograms per cubic meter. It's considered clean air. And so we no longer consider having a 40% chance of getting lung cancer healthy air. But this is so new. Right now, estimated that 4.5 million people are dying each year due to air pollution. So it dwarfs cholera, HIV, all the other diseases. Because it includes coronary disease, stroke, lung cancer, and COPD. And so I refer you to a Nature commentary 1 month ago, where this news is rapidly unfolding. Very, very deadly. Didn't know about it 5 years ago. Where does the PM2.5 come from? It comes from 2 sources mainly, coal plants and vehicle emissions. This is a picture of traffic in Beijing. You do not want to get stuck in rush hour in Beijing. And people talk about autonomous vehicles, but it's not the full solution. You think that with an autonomous vehicle in a major city like this, you can sit, you can open up a book, you can go on the internet, you can do things, and at least when your car is stalled, you're not emitting pollutants. But the real solution would be you need special lanes for electric buses and minibuses. And so once people see those buses and minibuses traveling 3 times faster than they are, they will get into those modes of transportation. Even rich people will want to travel faster. Okay, so let's go back to cheap wind, cheap solar. And in many parts of the world, 2 and 3 cents a kilowatt hour will be there. And it's going to open many exciting opportunities in electrochemistry. Let me tell you why. If you consider electrochemistry to split water, and you look at the thermodynamic limits, in this case, I'm showing the enthalpy, the amount of energy used to split water, 286 kilojoules per mole. The actual amount of energy is slightly less because there's an entropy help in getting water into 2 gas molecules. But it's, if you consider overpotentials, it's about this. So it's a good number. Here you have the thermodynamic limit, and on the x-axis you have the carbon-free costs it takes in dollars to create amount of hydrogen, a kilogram of hydrogen. And if electricity is 3 or 4 cents a kilowatt hour, then you're talking about the cost of energy being $1.50 per kilogram, which is about the rate of hydrogen around the world, $1.50 a kilogram. However, if the cost of electricity is 2 or 3 cents a kilowatt hour, let's say 2 cents, everything changes, because now the cost of electricity is half the cost of hydrogen. So if you can get an efficient way, electrochemical way of producing hydrogen, it's a good way. Now, what are the cost limitations besides electricity? Well, it turns out a major cost barrier for electrochemical production of any chemical is the size of the physical plant. It's the real estate. The precious metals used in current best catalysts of electrochemistry is a few % of the cost of the plant currently if you build one today. So it's actually real estate. And so to this end, we started thinking about how you can mimic nature to build a much more compact and efficient electrochemical plant. This work is led by Jun Lee, who's being co-directed by Yi Sui in material science at Stanford, and myself. So let me remind you of electrochemistry, something you do learn, I hope, in high school or grade school. You stick 2 electrodes, certain types, into water, you pass a current through, and lo and behold, you're turning water into hydrogen and oxygen. And so hydrogen and oxygen happily bubble up. And you put a membrane between those 2, you separate the 2 so the gases don't go kaboom. And so this is how you do it. And so here's the new idea. Just like a lung takes in air, oxygen, transfers the oxygen to the blood, and hemoglobin picks up the oxygen, carries the oxygen to the cells in the body. The cells metabolize, and they create metabolism products, water and CO2, just like burning fossil fuels. You're oxidizing sugars in this case, and really ATP. And the carbon dioxide gets carried by the blood back to the alveoli, these little sacs, where this biological membrane allows the carbon dioxide to freely diffuse back into the lung. Blood doesn't leak into the lung, and you exhale. So it's this transfer between gases both in and out that biology uses. So we looked at this and said, okay, if we can get a membrane, and a picture of this membrane is shown below. So these are 100 nanometer scale pores that readily pass gases back and forth, but they're hydrophobic. That means that that material really does not like water. So water does not penetrate. Even water at several atmospheres, 10 atmospheres, does not penetrate through these little pores. And so what happens is if you have your catalyst at the border of the water and it's connected electrically, you pass electricity through, the water looks around. Instead of making bubbles, the gas looks around and says, do I want to use a lot of energy to make a bubble, to expand against all this surface tension, or do I want to go through the membrane and go into a gaseous environment, a partial vacuum? And of course, you make the right choice because it costs less energy, so the oxygen goes in through the membrane. On the other side, you can get hydrogen evolution. How well does it work? Well, the red line is this polymer membrane with catalyst on it, and it is actually faster than the best commercial catalyst. But if we compare the catalyst we used with just a flat, planar structure, no porous membrane, no hydrophobic membrane, you have the gold. And so with very modest potentials, you begin to get very, very high current densities. Much lower energy, but you're not making bubbles, and you have intimate contact. Because the gases have limited solubility well, they're making bubbles. So that's good. If you want to design something, you could say, well, you can have planar structures where water is drawn up. In fact, if you just seal this, you get a free height of 32 feet of water height just because 1 atmosphere pressure supports that much water. You have electrolysis, and out of the water come oxygen and hydrogen. Since the system is sealed on the top, as you convert water into oxygen and hydrogen, it draws up more water. The surface is holding the electrocatalyst, and so for oxygen evolution, that's what you have. What about the water? If you wanted to make the electrochemical plant higher than 32 feet, you might use something that draws water up with capillary action. And so one of the materials we're considering is cellulose. There are cellulose materials that are designed to wick water very effectively. Other cellulose materials that wick water are trees. Redwood trees lift a single redwood tree can lift up to 2 tons of water a day to very high heights. In fact, the height of a redwood tree, about less than 400 feet, is limited by the capillary forces that are drawing water up the tree, getting to the leaves. The water is transpired, half of it's transpired through the leaves, or much of it is, and that draws more water. So, kind of free water pump due to capillary action. Why is this form of electrochemistry exciting? Well, you can look at the dimensions. Because you're moving gases, the spaces between the electrodes can be a fraction of a millimeter. The height of the electrodes can be tens of meters high. And all of a sudden, the footprint of electrochemistry shrinks dramatically because it's beginning to look like 3D electrochemistry, which was the major cost of the electrochemical plant. So because you have cheap electricity and the real estate goes down, this becomes very, very thinkable. That is to say, you have hydrogen and oxygen, both very useful for clean energy. We've shown the same to be true of carbon dioxide reduction, also world record catalytic rates. That is to say, better than anything on the market. And in this case, a very high fraction of carbon monoxide to hydrogen at the right potential. So again, very exciting. Now, in addition to that, I'm not going to talk about the exciting things happening in material science, but there are new materials called metal organic frameworks. These are these little structures in blue and green. And to that, you can add molecules, amine molecules, that are stuck there in blue. And when carbon dioxide looks at those molecules, it's readily absorbed. But because there's a phase transition between these so-called amine molecules and the carbon dioxide, it's a phase transition where you can begin to tailor the metal organic framework and the structure so a very small pressure swing can be the difference between absorbing carbon dioxide and emitting carbon dioxide, or a very small temperature swing. That means you can begin to absorb carbon dioxide, re-emit it, and collect it by absorbing it for carbon capture at perhaps half the cost or even less, maybe 1/3 the cost of absorbing carbon dioxide in liquid amines. We also need this to capture the carbon dioxide from existing fossil fuel plants, but there's more than just fossil fuel, because you have cement production, steel, petrochemicals, the whole lot. Cement production creates carbon dioxide just from converting limestone to calcium carbonate, but it's done at very high temperatures. So you need we use now fossil fuels to do that. The amount of carbon dioxide from cement production is staggering. It's 1.5 gigatons a year out of the 33 gigatons total carbon dioxide emission in the world. And you think 1.5 gigatons a year is staggering. One country is emitting 1.2 gigatons a year, China, because it's building so much. And when India's economy begins to turn on, as it's doing, it too will start to emit much carbon dioxide. And so we need to capture, until we get a replacement for limestone to concrete, we need to capture carbon dioxide. So let me end with a challenge for the 21st century, and that is that we want to produce liquid hydrocarbons from splitting water and reducing carbon dioxide. Essentially, that means you're reversing the combustion process. The products of combustion, typically with carbon fuels, is CO2 and water. So whatever means you have, thermochemical, electrochemical, photochemical, biochemical, can you begin to build the building blocks, hydrogen, carbon monoxide, and oxygen, and continue to build them to build a liquid hydrocarbon? What's so precious about a liquid hydrocarbon? Well, the energy storage per unit weight is maybe 40 times better than the foreseeable batteries in the coming decades. 40 times. And here's another advantage. This is a supertanker. And if I ask how much does it cost to ship crude oil and store it around the world in these big oil tanks you see near cities, on a cents per gallon of gasoline rate, the answer is 2 cents a gallon. Nearly free. Nearly free means we get to ship chickens in the United States anywhere around the world. We can get to ship corn and wheat, and you can ship coal and steel, iron ore to China. They make the steel, they ship it back as steel products, and it's cheaper than steel in the United States. Shipping is, unfortunately, very inexpensive. But think of it, unfortunately, because that means we ship a lot of stuff and burn a lot of carbon shipping it. But oil tankers are the transcontinental energy transmission lines because it is so inexpensive. So let me end by reminding you of one of my favorite pictures, taken Christmas Eve, 1968. So the astronaut who took the picture said, "We came all this way to explore the moon. And the most important thing is we've discovered the Earth." So look at this picture. The moon is not a good place to live. From this vantage point, Earth looks really good. And notice black all around, nowhere else to go. Not Mars. It doesn't have much air or water, and you get a lethal dose of radiation on the trip. Other than that, it's fine. And so since 1968, we've discovered that the climate of the planet is changing, and it's in large part due to humans. And so we better take heed of that and try to mitigate those changes, because this is our only home. Thank you.